The Tibetan Plateau is a hostile expanse of high-altitude rock. Deep within the Yellow River Gorge, engineers are completing the Yangqiu Hydropower Station. The main structure is a concrete face rockfill dam. It stands roughly 180 meters high, wedged tightly into the canyon bedrock. This is a 1.2 gigawatt facility. Once fully operational, it will generate 5 billion kilowatt-hours of electricity every year, supplying power to nearly 100 million people in Henan province. By late 2024, the primary electromechanical installations and core structural assembly were finished. Yet throughout the active construction phase, the core zones contained 0 human operators. At Yangqiu, the primary earth-moving and compaction tasks are no longer human-led. By shifting operators out of the machine cabs, engineers have replaced on-site manual coordination with a centralized automated framework for the core structural assembly. Researchers at Tsinghua University who designed the system described the construction of the Yangqiu Dam as a massive application of additive manufacturing. Traditional 3D printed architecture operates on a much smaller scale. A gantry system meticulously extrudes a continuous wet bead of concrete to form smooth curves like those of this office building. Applying this to a high-altitude megaproject requires stripping the concept down to its core logic. Additive manufacturing is the organizational process of building physical objects layer by layer directly from a digital model. At Yangqiu, the system treats thousands of tons of raw, unpredictable rock and soil as the printable material. A central artificial intelligence coordinates the entire operation. It turns a sprawling 180-meter high-altitude worksite into a singular, self-coordinating 3D assembly line. The central AI functions as an invisible conductor, dictating every mechanical action on the site. The workflow begins with digital slicing. The AI cuts a 3D dam model into thousands of horizontal layers. For each slice, it calculates the exact volume and material ratio required, then maps optimal transport roads for every autonomous vehicle based on the topography below. This centralized traffic control ensures that unmanned trucks never collide, maintaining a continuous, mathematically optimized delivery of rock and earth. By digitizing the workflow, the system removes the human foreman. Complex site logistics translate into pure, executable, algorithmic scheduling. With the schedule set, a fleet of unmanned heavy machinery acts as the mechanical effector organs for the digital instructions. Massive unmanned excavators begin the extraction phase at peripheral quarry sites, loading raw rock into autonomous transport trucks. During the transport phase, these trucks strictly follow the AI's pre-calculated routes to deliver their payload exactly to the active structural layer. Once delivered, autonomous bulldozers and pavers take over the deposition phase, spreading the material across the surface. The bulldozers must level the rock fill to the exact millimeter thickness calculated during the initial digital slicing. These vehicles possess no independent agency. They are the physical extruder heads of a macro-scale printing process, bound entirely to the digital model. Once a layer is laid down, it has to be compacted. In traditional embankment construction, the human operation of compaction rollers is a major vulnerability. A human driver might lay a layer too thick or drift off a straight trajectory. Over decades, these inconsistencies become subtle structural weak points. Yangqiu addresses this with robotic rollers equipped with satellite navigation receivers and an array of high-precision sensors. As the rollers crush the earth, they gather exact telemetry, measuring the vibration frequency, moisture content, and the physical resistance. This creates an instantaneous feedback loop, transmitting telemetry directly to the central scheduling system in real time. The algorithm enforces a strict rule. The AI must mathematically validate that the current layer meets the specified engineering density before triggering the next slice. This closed-loop telemetry allows the system to ensure structural integrity by removing the variables of human fatigue or inconsistent technique. The necessity of extreme automation is driven by the geographic reality of the Tibetan Plateau, known as the Third Pole. It sits where the Indian and Eurasian tectonic plates converge, creating a region of severe seismic risk. Holding back a massive reservoir in an earthquake zone leaves zero margin for error. A single human mistake in compaction is an unacceptable risk. The second driver for automation is demographic. China's working-age population is shrinking, prompting the Made in China 2025 policy to accelerate robotic substitution. At 3,000 meters, human workers face severe hypoxia and extreme temperature fluctuations. A machine maintains consistent operational thresholds regardless of the thin air. Recruiting and retaining a human workforce to operate heavy machinery in these remote gorges has become prohibitively expensive and biologically difficult. Autonomous worksites are moving from experimental luxury to a demographic and geographic necessity for sustaining critical infrastructure. In November 2024, the Yangkou hydropower station provided a definitive proof of concept. After passing all structural tests, the facility successfully connected its first generating unit to the state grid. This chart illustrates the leap. Compared to milestones like the 20-foot Dubai office and 86-foot Shanghai bridge, the 590-foot Yangkou Dam dwarfs them. This proves volume is no longer the limitation. The barrier was software coordination, which Yangkou's algorithms addressed. This organizational logic is already being applied to other sites. Construction has begun on the 2.2 gigawatt Yebaton Dam using a similar hybrid model. The success at Yangkou provides a verified blueprint for infrastructure in hazardous environments. It demonstrates that autonomous fleets can handle high-volume structural tasks in remote regions where recruiting a human workforce is becoming increasingly difficult. The ability to rapidly construct automated dams on the Tibetan Plateau creates immediate geopolitical friction, particularly for downstream nations. India and Bangladesh harbor fears that this advanced infrastructure could be used to restrict essential water flows or release sudden floods during regional conflicts. This political dynamic is known as hydrohegemony. Unilateral, rapid dam building acts as a mechanism for a state to assert authority and control over international water resources. Long-term, the applications for this AI coordination extend to entirely lethal environments, from deep-sea energy facilities to utilizing local regolith to build lunar habitats. The Yangkou Dam shows that massive embankment projects can now function without operators in the core construction zones. It moves the burden of structural validation from human oversight to the consistent, sensor-driven data loops of an autonomous fleet.